Imagine standing on the edge of everything, staring into the infinite unknown where space doesn't end with a wall or a barrier, but instead stretches out into something we may never truly grasp, a vast cosmic frontier that has haunted the dreams of scientists, philosophers, and poets alike. Because to understand the edge of the universe is to confront the limits of human comprehension itself, a task so audacious that it challenges not only what we know but how we know it. And yet, despite our smallness in this grand celestial ocean, we continue to ask questions. We continue to build telescopes that peer deeper into space and further back in time, searching for clues in the oldest light, decoding messages that have traveled billions of years just to reach us, hoping they whisper secrets about where it all began and where it might end, if it even ends at all. Because the idea that the universe might have an edge is not just a scientific inquiry, it's a philosophical provocation, a challenge to everything we think we understand about reality. Because if there is an edge, then what lies beyond? And if there isn't, then how can something be endless? And if space is expanding, then what is it expanding into? And as you sit here, wherever you are, maybe wrapped in a blanket, maybe lying in bed trying to fall asleep, or maybe just scrolling through in the quiet hours of the night, realize that you are part of this mystery. Because the atoms in your body were forged in ancient stars, the calcium in your bones, the iron in your blood, the carbon that forms the very basis of your life, all came from explosions billions of years ago, scattering stardust across the cosmos. And somehow that stardust organized itself into you, a being capable of wondering, capable of observing, capable of looking up and asking why. And that act of questioning is what makes us uniquely human, what separates us from the silent void, what gives this endless dark a sense of meaning. And as we try to map the edges of a universe that might not have any, we also map the boundaries of our own understanding, pushing them further with each discovery, each experiment, each new piece of data. And right now, as you hear these words, humanity is closer than it's ever been to uncovering what lies beyond the veil of our known universe, thanks to powerful tools like the James Webb Space Telescope that lets us see further into the past than ever before, and cutting-edge physics that dares to challenge the very fabric of space-time, proposing theories like the multiverse, brain cosmology, and the holographic principle, each offering radically different answers to the question of what lies beyond the observable edge, and yet each grounded in equations that, while elegant, leave us with even deeper questions. Because the edge of the universe is not just a place in space, it's a concept wrapped in paradox, a riddle that may never yield to direct observation, and yet it calls to us, a cosmic siren song that lures the minds of dreamers and scientists alike into the most profound explorations, into thoughts that transcend the limits of language and take us to the borderlands of the possible, where space curves and time warps, where the rules of physics themselves may bend or break, and where the truth might be more beautiful and strange than we ever imagined. And in the heart of that mystery is a quiet but relentless drive to understand. Because to know what the universe is, what it contains, and how it ends, or whether it loops back on itself or stretches forever, is not just to understand the cosmos, it is to understand ourselves. Because our stories, our myths, our religions, and even our technologies are all born from the need to explain what we see in the night sky. And every new answer brings with it 1,000 more questions, spinning out into infinity like the galaxies we can barely see. And so, if you've ever looked up and felt something stir inside you, something ancient and unexplainable, something like awe or longing, or a deep sense of connection to something greater, then you are already part of this story. And if this journey through space and time sparks even the tiniest ember of curiosity in you, then make sure to like this video, subscribe for more mind-expanding explorations, and drop your thoughts in the comments, because your questions matter, your wonder matters, and together we'll dive into the biggest mysteries of the cosmos, one discovery at a time. And who knows, maybe the edge of the universe isn't just out there in some distant galaxy beyond the reach of our eyes and instruments. Maybe it's also within us, at the edges of what we believe is possible, waiting to be redefined by the next person, bold enough to ask the impossible. For most of human history, the night sky was not just a backdrop to our existence, but a canvas upon which ancient civilizations projected their myths, fears, and questions. For long before telescopes or satellites, early humans stared up at the stars and wondered what they were, imagining them as gods, spirits, or lanterns fixed to a celestial dome. And in that wondering, the seeds of astronomy were planted, first as a spiritual quest and later as a scientific endeavor, as cultures like the Babylonians, Egyptians, and Mayans began tracking celestial movements, predicting eclipses, and aligning their monuments with the stars. Each step a quiet revolution that moved us closer to understanding our place in the cosmos. And yet, even these early observations were bound by the idea that Earth was the center of everything, a belief that persisted for centuries, upheld by thinkers like Ptolemy, who in the 2nd century CE refined the geocentric model into a complex system of deferents and epicycles that described planetary motion with impressive accuracy, but ultimately masked the truth, because it would take a paradigm shift to break this Earth-centered illusion. And that shift came in the 16th century with Nicolaus Copernicus, who dared to suggest that the Sunday, not Earth, was at the center of the solar system, a heliocentric idea that at first seemed absurd and even heretical, but eventually reshaped the entire foundation of astronomy, especially when Galileo Galilei, using one of the first telescopes, observed moons orbiting Jupiter and phases of Venus that could only be explained by the Copernican model. And although he faced persecution for his views, the evidence was undeniable, setting the stage for Johannes Kepler to refine the motions of the planets into elliptical orbits, and Isaac Newton to reveal the universal force behind it all: gravity. A force that not only explained planetary motion but hinted at deeper laws governing the entire universe. And as Newton's equations reigned for centuries, predicting everything from falling apples to the paths of comets, they also laid the groundwork for something far more profound: a new way of seeing the universe, not as a static machine, but as a dynamic, evolving entity, an idea that would be taken to astonishing new heights in the 20th century, with the birth of modern cosmology, beginning with Albert Einstein's general theory of relativity in 1915, which replaced Newtonian gravity with a vision of space-time as a flexible fabric warped by mass and energy, leading to predictions like black holes and the bending of light around massive objects, both of which have since been confirmed through observation. And yet Einstein himself was reluctant to accept one consequence of his equations: that the universe was not static but must be expanding or contracting, a notion so troubling that he added a cosmological constant to force his equations to describe a stable universe, a move he later called his greatest blunder, because in the 1920s, Edwin Hubble's observations of distant galaxies showed that they were moving away from us, and that the farther they were, the faster they receded, implying that the universe was indeed expanding, a discovery that transformed our understanding of cosmic history and gave rise to the Big Bang Theory, the idea that the universe began as a singularity, a point of infinite density and temperature approximately 13.8 billion years ago, and has been expanding ever since. A theory further supported by the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson, which captured the faint afterglow of the early universe and confirmed predictions made by physicists like George Gamow decades earlier. And as technology advanced, so too did our ability to peer deeper into this cosmic past, with missions like COBE, WMAP, and Planck mapping the microwave background in exquisite detail, revealing subtle temperature fluctuations that trace the seeds of all future structure of galaxies, clusters, superclusters, that formed under the influence of gravity. And yet, for all we've uncovered, the observable universe remains just that. Observable, limited by the speed of light and the age of the cosmos, meaning that there are regions of the universe so distant that their light has not yet had time to reach us, creating a spherical horizon around us some 46.5 billion light-years in radius, not because that's the true edge of the universe, but because that's as far as we can see, bounded by the finite time light has had to travel since the Big Bang. And as we push that boundary with ever more powerful instruments like the Hubble Space Telescope and its successor, the James Webb Space Telescope, we are not only extending the observable universe, but also challenging the assumptions we've long held about it. Because discoveries like the accelerating expansion of the universe revealed by studying Type Ia supernovae in the late 1990s shave introduced the concept of dark energy, a mysterious force driving galaxies apart faster over time and suggesting a universe whose fate may be one of eternal expansion, growing colder and more diffuse as stars burn out and black holes evaporate. And alongside this is the equally enigmatic presence of dark matter, an invisible substance that outweighs normal matter 5 to 1 and holds galaxies together with its gravitational grip, despite being undetectable by direct means, known only through its gravitational effects. And these twin mysteries, dark matter and dark energy, now dominate modern cosmology, shaping our models and pushing physicists to consider theories beyond the standard model of particle physics, including supersymmetry, extra dimensions, and quantum gravity, each an attempt to bridge the gap between the very large and the very small, between general relativity and quantum mechanics, which remain incompatible despite a century of effort. And yet this tension has sparked some of the most creative and daring ideas in science, such as the possibility of a multiverse, born from the inflationary epoch believed to have occurred just moments after the Big Bang, when space itself expanded faster than the speed of light, smoothing out the universe and explaining its uniformity, but also possibly spawning countless other bubble universes with different physical constants, forever beyond our observational reach. And while these ideas remain speculative, they are rooted in serious mathematics and increasingly guide our interpretation of the data. And meanwhile, space exploration has expanded our physical reach, from the early achievements of Sputnik and Apollo to the robotic explorers like Voyager 1 and 2, now venturing through interstellar space and missions to Mars, Saturn, and beyond, each one revealing new wonders and deepening our appreciation of the cosmic scale. And today, with private spaceflight becoming a reality and international efforts aiming toward a return to the Moon and eventually Mars, humanity stands at the edge of a new era, one in which we may one day look back on our tiny, fragile planet from the vantage of distant worlds, carrying with us not just the tools of survival, but the legacy of our curiosity, a legacy that stretches back through centuries of observation, conflict, revelation, and awe, and all of it, every theory, every telescope, every line of code and flash of insight has led us to this moment where we can look up at the sky and not only see stars, but understand, at least in part, what they are, how they came to be, and what their existence means for us. And yet, despite all we've learned, the greatest mystery may still lie ahead. What lies beyond the observable universe, whether it ends or wraps around, whether time itself is linear or loops, and whether space has edges or is infinite in every direction. And to face these questions is to embrace both humility and wonder, because we are still the same species that once thought the stars were gods, and yet now we chase the origin of everything with machines and mathematics, guided not by myth, but by evidence. And still, the night sky continues to inspire the same awe it did thousands of years ago, reminding us that the journey from myth to measurement is not an end but a beginning, the foundation of a story still being written, one discovery at a time. There's a moment, maybe you felt it, when you look up at the night sky and it's so quiet, so endless, that something deep inside you stirs, something ancient and inexplicable, a strange mix of awe and longing, and the faintest echo of fear. Because in that darkness above is not just a scattering of stars, but the raw, unfiltered face of the infinite. And it stares back at you with a silence so absolute it almost speaks, reminding you of just how small you are and just how vast everything else might be. And yet, that feeling, that quiet confrontation with the unknown, is one of the most human things you can experience. Because for as long as we've walked this earth, we've looked to the heavens not just to navigate our ships or plant our crops, but to ask the deepest questions we can form. Why are we here? Where did we come from? What happens when we die? And is there something out there greater than all of this? Something watching, something waiting? Or are we truly alone in this cold expanse, spinning through a darkness without edges or purpose? And if that's true, then what does it mean? And yet, even in that terrifying possibility, there is a strange kind of beauty, because if the universe really is indifferent, if we are truly alone in all this unimaginable emptiness, then every act of kindness, every spark of love, every fragile human connection becomes infinitely more precious because it's ours, because we made it in defiance of the void. And in that defiance lies our greatest strength, our ability not only to survive, but to wonder, to dream, to look out into the blackness and not just see emptiness, but possibility. To see not just stars, but stories. Not just galaxies, but potential futures. And that is why this matters not because space is big, though it is, not because it's beautiful, though it's breathtaking, but because in exploring it, we learn what it means to be human, because the cosmos doesn't just exist out there, it lives in us, in our questions, in our restlessness, in our refusal to stop searching. And when you think about it, that's what drives every great breakthrough, every mission, every experiment, every telescope pointed at the sky. Because behind all the equations and data and engineering is a simple truth. We want to know. We need to know. And that need isn't just scientific. It's spiritual. It's emotional. It's wired into our very being. Because how can we live a full life if we don't try to understand the world we're living in? And isn't that what drives so much of what we do, this endless desire to make sense of the chaos, to find order, meaning, connection, to carve a path through the unknown even if we never reach the end? Because the edge of the universe is not just a place, it's a metaphor. It's the boundary of what we know. And crossing that boundary, even in thought, even in story, gives us hope that there is more, that we can be more, that the universe, for all its silence, might just be listening, or if not, that we might still find meaning in the echo of our own questions. And it's that echo that drives people to build rockets, to launch telescopes, to spend years studying invisible forces and distant light, because they're not just chasing facts, they're chasing wonder, chasing that feeling you had when you were a kid lying in the grass, staring at the stars, imagining what might be out there. And somewhere along the way, many of us forget that feeling. We get busy, we get tired, we get pulled into the noise of daily life, but it never really leaves us. That spark, that curiosity, that ache to know more. And that's why space matters. Because it calls that spark back to life, it makes us feel small in the best way possible. Not insignificant, but part of something bigger, part of a grand unfolding that has been going on for billions of years and will continue long after we're gone. And in that cosmic timeline, we are a blink, a flicker. And yet, what a flicker it is, because in this tiny moment we call human history, we've built cities, written symphonies, fallen in love, created art, walked on the moon, sent machines to the edge of the solar system, and started to understand the very code of the universe itself. And that should make you feel something: pride, humility, maybe a little fear, but above all, wonder, because that is the feeling that connects all of us, no matter who you are or where you come from, whether you believe in science, in religion, in fate, or randomness, because we all live under the same sky. We all share the same cosmic origin, and in that shared origin is a quiet truth. We are one species, one people, floating together on a pale blue dot in a sea of stars. And if we can remember that, if we can hold on to that perspective even for a moment, then maybe we'll treat each other with a little more kindness, live with a little more purpose, dream with a little more courage. Because in the face of a universe so vast and so unknowable, the only thing more remarkable than the cosmos is the fact that we are here, that we are aware, that we can wonder at all. And so as you sit here now, maybe watching this in bed, maybe with your headphones in while the world outside sleeps, know this: you are part of something beautiful, something ancient and still unfolding. And the questions you carry, the ones about life, about purpose, about what lies beyond those questions, are the same ones that have echoed through every generation. And asking them makes you part of a long, noble tradition of seekers, dreamers, explorers, and lovers of truth. And maybe we'll never have all the answers. Maybe the edge of the universe will always lie just beyond our reach. But even so, we'll keep reaching, not because we expect to grasp infinity, but because in the reaching we become more than we were. we transcend the limits of what we thought possible. And we remind ourselves that in a universe ruled by entropy, the very act of reaching is a form of creation, a spark of light in the darkness, a story still being told. And that story, the story of us, of Earth, of life, of wonder and discovery, is worth everything. And if that resonates with you, if some part of you feels the pull of those stars, then let that feeling grow, let it guide you. Because that curiosity you feel, it's not a distraction from life, it is life. It's the pulse of something deeper that connects you not just to the universe, but to every other person who's ever looked up and wondered. And if that's not worth caring about, what is? What if everything you've ever believed about the world, about time, about space, about reality itself was just a small fragment of a much bigger, stranger truth waiting to be uncovered? And what if that truth was already unfolding silently in the background of your everyday life, hidden in the deep sky, encoded in the flickering light of ancient galaxies, and written into the invisible laws that govern every atom of your body? What if the questions you've asked late at night, when the world is quiet and the stars are bright, weren't just philosophical daydreams, but clues, real, meaningful signs that your mind is capable of reaching far beyond the surface of things and brushing against the very structure of the cosmos? When you look up at the sky and feel that strange pull in your chest, that aching curiosity, that sense that there's more to existence than what we can see and touch, you're not alone. That feeling is ancient, universal, and shared by every thinker, dreamer, and explorer who's ever dared to challenge what we think we know. And in this moment, as you listen or watch or read, you are now part of that journey. Because asking questions is not passive, it's revolutionary. It's the first step toward discovery. And every time you wonder, what if, or how, you are lighting a match in the dark, one that might grow into a fire of understanding that reshapes not just your view of the world, but the world itself. So, let me ask you now, what do you believe lies beyond the edge of the observable universe? Do you think space is infinite, stretching forever without end? Or does it curve back on itself, folding into something we can't yet imagine? Do you believe there are other universes, whole realms with different laws of physics, where time flows differently, or where stars never formed, or maybe where intelligent life has evolved in ways so alien we couldn't even recognize it? And if those universes exist, what does that mean for us? Are we special, or are we just one flicker in a sea of infinite variation? And if the universe is finite, if there really is an edge, what lies beyond it? Nothingness, something else, or the very structure of existence breaking down? These aren't just abstract questions for scientists and labs. They're questions that hit at the core of who we are and what this all means. Because the shape and fate of the universe affects how we think about life, death, meaning, connection, even morality. If the cosmos has no edge, does that suggest endless possibility? If it does, is there a boundary to what we can achieve? To what we can become? If reality itself is shaped by unseen forces like dark energy or quantum fluctuations, then what does that mean for free will, for consciousness, for the very idea of you? Could it be that your thoughts, your dreams, your memories are not just biological processes, but ripples in the fabric of something deeper, something we don't yet have words for? And what happens when we finally learn the answers to these questions? Will it change the way we live, the way we relate to one another, the way we define progress, success, happiness? Imagine waking up one morning to the news that we've detected undeniable signs of intelligent life in another galaxy. How would that shift your view of humanity, of conflict, of purpose? Would our differences still matter as much? Or would we unite in awe and fear and hope, facing the truth that we are not alone? Or what if we discover evidence that the universe is a hologram, a projection of information from a deeper reality? Would you process that, knowing that everything you touch and see and feel might be a shadow of something more fundamental? These questions might sound like science fiction, but they are grounded in serious inquiry, real data, and the frontier of modern physics. And the answers, if we find them, could transform not just science, but culture, philosophy, religion, and art, because they strike at the heart of the human story, the one we've been writing since we first painted the stars on cave walls and told stories around fires about the gods above. And today, you are part of that story, not as a passive observer, but as an active participant, because you are here, asking, wondering, engaging, and your thoughts matter, your questions matter, your voice matters. So share them, leave a comment. Tell us what you think lies beyond the edge of space, what your biggest cosmic question is, what scares you, what excites you, what keeps you up at night when you stare into the dark and feel that strange sense of something greater pulling at your soul. Start a discussion, challenge ideas, propose your own theories, or just share what the universe makes you feel. Because this isn't just about facts and figures, it's about meaning, about connection, about coming together in our shared wonder to explore the biggest questions of all. And when you engage with these mysteries, you're not just learning, you're helping to shape the future of knowledge itself. Because the more we talk about this, the more curiosity spreads. And curiosity is the fuel of discovery, the engine of progress, the one thing that keeps us growing even when the answers seem impossibly far away. So don't just watch, respond. Don't just consume, create. Let your imagination run wild. Because sometimes the questions you ask will lead to breakthroughs no one's ever considered. And sometimes, just the act of wondering is powerful enough to change your whole perspective. The universe is not a closed book, it's an open invitation, a question mark stretching across the sky, waiting for minds like yours to pick up the pen and write the next line. So whether you're a student, a scientist, a dreamer, or someone who's never thought much about space until now, this is your chance to dive deeper, to explore the mystery not just with your mind, but with your heart. Because science isn't just equations and experiments, it's a human endeavor, driven by emotion, by fear, by hope, by the relentless need to understand where we are, how we got here, and what comes next. And in a world that often feels chaotic, divisive, and uncertain, the night sky remains a constant, a quiet reminder that there is still so much to discover, so much to unite us, so much to inspire us. And it starts with one simple act, asking a question. So I ask you again, what do you think is out there? What do you hope we'll find? And how will the answer shape the story of us all? Join the conversation. Let's wonder together. Let's ask the impossible. And maybe, just maybe, we'll be the generation that dares to find out. Close your eyes for a moment and imagine drifting far beyond Earth, past the flicker of city lights, past the swirling blue marble we call home, past the moon, past the shimmering orbits of artificial satellites and forgotten space probes, past the rings of Saturn and the icy silence of Pluto's distant path. Now, imagine you've left the solar system entirely, and ahead of you stretches the raw expanse of interstellar space, a place so empty and so vast that even light takes years, centuries, millennia to cross from one point to the next. Out here, there is no sound, no air to carry it. Only the gentle hum of cosmic radiation and the silent glow of stars, so distant they appear frozen in time. You float through this infinite ocean, surrounded by the scattered jewels of the Milky Way, a barred spiral galaxy with arms of stardust curling like celestial waves across 100,000 light-years, housing billions of stars, each with its own story, its own system, its own mystery. And yet the Milky Way is just one of hundreds of billions of galaxies, each spinning, colliding, birthing stars, and fading into silence across a universe that stretches some 93 billion light-years in observable width. Between these galaxies lie vast regions of emptiness called void cements, cosmic gaps, where gravity hasn't pulled matter together, where even light is sparse, where the loneliness is almost unbearable. And it's here, in this delicate balance between light and darkness, that you begin to feel the true scale of reality. Within these galaxies are nebulae, clouds of gas and dust, so massive they span light years, cradling the birth of stars within their glowing arms. Some glow red and orange with the heat of newborn suns, while others, like the Eagle Nebula's pillars of creation, stand like towers in the night, vast, cold, and majestic, shaped by the invisible hand of radiation and time. Nearby, black holes lurk, regions of space-time so warped by gravity that nothing, not even light, can escape. And around them whirl disks of matter heated to extremes, releasing energy that can outshine entire galaxies. These black holes are not just terrifying, they're fundamental, shaping galaxies, bending time, and perhaps even providing bridges to other universes, if the laws of physics allow such things. And then there is dark matter, the invisible scaffolding upon which all this luminous beauty is built. Though we cannot see it, touch it, or detect it directly, its presence is undeniable. Galaxies rotate faster than they should, galaxy clusters stay bound despite their mass, and gravitational lensing reveals the weight of something we cannot explain. It is dark, matter-silent, unseen, mysterious, and it outweighs all the stars, planets, and visible dust combined. Alongside it exists an even more puzzling force: dark energy, a pressure embedded in space itself that accelerates the expansion of the universe, as if the cosmos is being pushed apart faster and faster with each passing second, and we don't yet know why. These are not just distant curiosities, they are the threads that weave the tapestry of the universe, and through them runs the same force that forged us. The iron in your blood, the calcium in your bones, the oxygen you breathe all were born in the cores of dying stars and scattered across the galaxy by supernovae billions of years ago. You are, quite literally, made of stardust, a walking collection of cosmic debris arranged by time and chance into the miracle of consciousness. And while that might sound poetic, it is also scientifically accurate. This connection to the universe is not abstract, it is elemental. It is intimate. It is you. And who are the minds that guide us through this cosmic labyrinth? Giants like Edwin Hubble, who first showed us that the universe is expanding, forever changing our view of the cosmos. Albert Einstein, whose equations of general relativity bent our understanding of space and time into something dynamic, alive, and strange. Vera Rubin, who watched galaxies spin too fast and inferred the presence of dark matter long before it was widely accepted. Stephen Hawking, who dared to unite quantum mechanics with gravity in the most extreme environments imaginable, black holes. And today, names like Brian Greene, Lisa Randall, Neil deGrasse Tyson, Katie Mack, and Sean Carroll continue to push the boundaries of what we know, using mathematics, theory, and observation to unlock doors we didn't even know existed. They are not just scientists, they are storytellers of the universe, translating the cold data of telescopes into narratives of creation, destruction, time, and eternity. And the tools they wield are equally awe-inspiring. The James Webb Space Telescope, floating 1 million miles from Earth, unfolding its golden mirrors to glimpse the earliest galaxies, seeing light that has traveled 13.5 billion years. The Event Horizon Telescope, an Earth-sized array that captured the first image of a black hole's shadow, confirming decades of theory. Particle accelerators, like CERN's Large Hadron Collider, smashing atoms at near-light speeds to understand the fundamental particles that make up everything, hoping to glimpse the fabric of space-time itself unravel. These instruments are our eyes and ears in a cosmos that doesn't speak in words, only in radiation and gravity and time. And the tone of this exploration, this endless search for meaning and mechanism, is a strange harmony of emotions. There is awe, of course, that primal emotion that leaves you breathless before the sheer scale and beauty of the universe. There is mystery, the unspoken thrill of not knowing, of staring into the darkness and wondering what's out there. There is curiosity, a tireless energy that refuses to settle for easy answers, that asks again and again, why, how, what else? But there is also humility, because the more we learn, the more we realize how little we understand. The deeper we look into the cosmos, the more it reveals a complexity that challenges our models, breaks our expectations, and reminds us that we are not the masters of this place, but explorers, temporary visitors, trying to understand an ancient and ongoing story. This atmosphere, the emotional, intellectual, and visual immersion into space is what drives not just science, but imagination. It's why people write novels about space travel, why filmmakers build entire sagas about distant galaxies, why musicians compose symphonies inspired by the stars, and why children still dream of becoming astronauts. Because the universe is not just out there, it's in us. It's part of our identity, part of our cultural DNA, part of the mythos we've always needed to make sense of life. And in moments of quiet reflection, when we are alone with our thoughts, that cosmic silence often returns not to scare us, but to remind us of our roots and of our destiny. So when we talk about galaxies, We're not just listing facts, we're imagining colossal cities of stars, billions strong, orbiting one another in slow, majestic dances. When we speak of voids, we're not just describing empty space, we're contemplating regions so barren they defy comprehension, where light has never passed, and matter is a rumor. When we explore concepts like the Big Bang, inflation, or the heat death of the universe, we're not just using scientific terms, we're narrating the life cycle of everything, from the first spark to the final silence. These ideas are not dry, they are vibrant. They are thrilling. They are the truest epic we know. And as we drift through this narrative, surrounded by cosmic dust, neutron stars, quasars, and superclusters, let us not forget the Earth beneath USA, fragile outpost clinging to life in an otherwise hostile universe. A singular blue sanctuary floating in a sea of fire and frost. It is here, on this tiny rock, that the universe has become conscious of itself. It is here that hydrogen, through time and gravity and luck, began to ask questions. It is here that matter formed memory, love, creativity, fear, and science. So let this atmosphere settle into you, the vastness, the silence, the beauty, the strange laws that bend light and slow time. Let the weight of cosmic history pass through you like starlight, and let the mystery fill you not with fear, but with wonder. Because in a universe where stars are born and die, where galaxies collide, and where black holes whisper the limits of known physics, we are not just spectators. We are the latest chapter in a story 13.8 billion years in the making. And that story is still unfolding. What if the greatest question we can ask is one we'll never answer, not because we lack intelligence, not because we don't try hard enough, but because the universe itself has built its most profound secrets behind walls we may never be able to scale? What if, despite all our telescopes, all our equations, and all our dreams, the true edge of the universe remains eternally hidden, not just in distance but in principle, cloaked in paradoxes that defy logic and laws that crack under the weight of infinity? This possibility doesn't just haunt the minds of cosmologists, it defines the cutting edge of modern science, and it suggests a conflict not between us and the cosmos, but between what exists and what can never be known. From the moment we realized the universe was expanding, we began chasing its limits, mapping the light from distant galaxies, measuring the redshift, calculating cosmic microwave background radiation, and running simulations that model the evolution of everything, from the first atomic nuclei to the formation of galactic clusters. And yet, the further we look, the more we're forced to confront a strange and frustrating reality. The observable universe is just a bubble, a horizon beyond which we cannot see, not because nothing is there, but because light from those places has not had enough time to reach us, and may never reach us, especially as space itself expands faster than that light can travel. This boundary, called the cosmological horizon, is not a physical edge, it's a limit imposed by the nature of spacetime itself. Beyond it may lie countless other galaxies, entire cosmic structures, even entire realities, but we will never observe them, never test them, never verify their existence in any empirical way. In that sense, the edge of the universe becomes not a wall, but a curtain, a veil of fundamental limitation that mocks our deepest questions. And what's more, the closer we get to these boundaries, the more our tools begin to fail, not mechanically, but conceptually. Our best theories, general relativity and quantum mechanics, work brilliantly within their domains, but they clash at the extremes, where black holes collapse to singularities, or the Big Bang compresses all of existence into an infinitely dense point. These singularities aren't just weird, they're warnings. They're signs that our understanding breaks down at the limits, that our maps end not with answers, but with paradoxes. Take time, for example. Is it a river that flows from past to future, or is it an illusion, a construct born of our limited perception? In relativity, time slows near massive objects, warps with gravity, and stretches across the expanding universe. In quantum theory, time is often treated as static, a backdrop for probabilities and entanglement. When we try to merge these two views, relativity's smooth geometry with quantum physics' discrete particles, we get mathematical nonsense, infinities that shouldn't be there, contradictions that refuse to be resolved. String theory tries to solve this by adding extra dimensions, sometimes 10, sometimes 11 or more, but those dimensions are curled up at scales we'll likely never probe. Loop quantum gravity offers a competing vision, suggesting space and time themselves are made of discrete loops, but its predictions remain hard to test. Meanwhile, the holographic principle suggests that everything inside the universe might be encoded on its surface, as if we're living inside a projection. But how do we verify something that implies our entire notion of space is a kind of illusion? And then there's inflation, the idea that in the earliest moments after the Big Bang, the universe expanded exponentially, smoothing out its structure and making everything we observe today possible. But inflation also predicts something more unsettling, that this process could be eternal, spawning infinite pocket universes with different physical laws. This multiverse isn't science fiction, it's a mathematical consequence of many leading theories, but it's also fundamentally untestable. If other universes exist but can never interact with ours, can we ever say anything meaningful about them? And if we can't test the multiverse, if we can't observe what lies beyond our cosmic horizon, then have we reached the edge of science itself? Are we doomed to peer into an ocean of possibilities without ever dipping our toes into the water? Even our instruments betray us. Light, our primary messenger, is slowed, redshifted, and scattered by time and distance. The further away we look, the older the universe becomes, until eventually we reach the cosmic microwave background, the surface of last scattering, beyond which lies only darkness, a fog that no light has pierced since the beginning of time. Beyond that lies the inflationary epoch, a time so energetic and brief that our physics breaks entirely, and before that, perhaps nothing at all, or something so foreign that our words, our math, our minds cannot grasp it. Every time we extend our reach, we find new layers of mystery, and in doing so, we often realize that we've misunderstood something fundamental. We once thought the universe was static, it's expanding. We once thought it was slowing down, it's accelerating. We once thought we understood matter. Now we know that 95% of the universe is made of dark matter and dark energy, neither of which we can explain. And what if the very way we're asking these questions is flawed? What if time and space, matter and energy aren't the bedrock of reality, but emergent phenomena, illusions that arise from something deeper, something timeless and spaceless and altogether alien to our experience? Theoretical physics is increasingly pointing in this direction, toward quantum information as the true substrate of existence, where reality behaves less like a machine and more like a computation, where the universe isn't just physical, it's logical. But if that's true, how do we even begin to explore it? Our brains evolved to throw spears, grow crops, build shelters, not to visualize 11-dimensional membranes or entangled superpositions across cosmic distances. We are clever apes, staring into the abyss, trying to turn it into a story we can understand. And sometimes, just sometimes, the abyss seems to whisper back, "You weren't built for this." But we keep asking, we keep pushing, because the conflict isn't a dead end, it's the pulse of discovery. Every paradox is a clue. Every limitation is an invitation to think differently. And while it's true that we may never find the true edge of the universe, that we may be forever limited by what we can observe and measure, it's also true that those very limitations have led us to our most profound breakthroughs. It was in the gaps between Newtonian physics and electromagnetism that relativity was born. It was in the confusion over atomic behavior that quantum theory emerged. And today, it is in the tension between gravity and quantum mechanics, between observation and theory, that the next revolution is waiting. Perhaps it will come from a new particle discovered at the edge of a collider's reach. Perhaps it will come from a strange pattern in the cosmic background radiation. Perhaps it will come from a mathematical insight in a quiet moment of brilliance. Or perhaps it will come from a place we never expected, from consciousness, from information theory, from philosophy, or even from technology we haven't yet imagined. And so the conflict at the heart of cosmology is not just about physics, it's about the limits of knowledge, the boundary between what is real and what is knowable, and the unsettling possibility that those two things may not fully overlap. We may live in a universe that hides its deepest truths, not out of cruelty, but because it has no choice. Reality may be structured in such a way that certain answers are forever outside our reach, like books we cannot open, written in a language we'll never learn. But even if that's true, even if the edge of the universe remains forever just out of sight, it does not diminish the beauty of the pursuit. In fact, it makes the pursuit even more heroic, because to chase the unreachable, to question the unanswerable, is to affirm something deeply human, that we are not content with shadows and guesses, that we will always seek light, no matter how distant, no matter how faint. And maybe that's the real point, not to reach the edge, but to understand why we can't, to find meaning not just in what we know, but in the act of reaching. Because in that reaching, we change, we grow, we become something greater than we were. The edge of the universe may never be a place we can point to on a map, but it is a mirror, reflecting the limits of our understanding and the endless courage it takes to confront them. Somewhere between the elegance of mathematical equations and the silence of the night sky lies a battlefield, not one of violence, but of ideas, of theories, of visions of reality that do not agree. And at the heart of this conflict is one of the greatest questions science has ever faced. Does the universe have an edge? And if so, what lies beyond it? For centuries, we imagined the cosmos as something finite and comprehensible, first with Earth at the center, later with the Sunday, and eventually with galaxies scattered in every direction. But as our tools and theories evolved, so did the magnitude of our questions, and what once seemed certain now trembles under the weight of contradiction. The struggle to define the edge of the universe is not a problem with a clear solution, but a war between different frameworks of understanding, each supported by evidence, yet each pulling reality in a different direction. And nowhere is this tension more visible than in the clash between general relativity and quantum mechanics, the two towering pillars of modern physics. General relativity, Einstein's masterpiece, paints a picture of the universe as a smooth, continuous fabric of space-time that bends and stretches under the influence of mass and energy. It tells us how planets orbit, how black holes form, how light is bent by gravity, and it has passed every observational test thrown at it, from the precession of Mercury to the recent detection of gravitational waves. But it also predicts singularities regions, where the curvature of space-time becomes infinite, such as the center of black holes or the beginning of the Big Bang. These singularities aren't just strange, they're devastating to the theory itself, signaling points where its predictions cease to make sense. On the other side, quantum mechanics offers a radically different view, where particles behave like waves, uncertainty rules, and events are governed by probabilities, not certainties. Quantum theory explains the behavior of atoms, the structure of matter, and underlies all of modern electronics. Yet when it's brought into the realm of gravity, it breaks. The two theories, both immensely successful in their own domains, refuse to unify at the extremes, and it's precisely at those extremes, at the edge of the universe, where we need them most. This theoretical clash is made worse by the competing explanations for the shape and fate of the universe itself. Is it finite, like the surface of a sphere, with no edges but a defined volume? Or is it infinite, stretching endlessly in all directions, without beginning or end? Both models are supported by different interpretations of the data. The observable universe is finite to roughly 93 billion light-years across, simply because light has only had so much time to reach us since the Big Bang. But that doesn't mean the universe itself is finite. It could stretch far beyond that visible boundary, perhaps infinitely, or it could loop back on itself in a higher dimensional curvature, like a 3D version of the Earth's surface, where traveling far enough in one direction could eventually bring you back to your starting point. And here lies the rub. We may never be able to measure it. If the universe is infinite, we'll never see its edge. If it's curved back on itself on a scale much larger than our horizon, we won't detect the curvature. Our measurements of cosmic background radiation and galaxy distribution suggest that the universe is flat, but flatness is consistent with both infinite and very large finite models. We are, in effect, trapped inside a bubble of light, trying to guess the shape of the world beyond by analyzing only a small part of it. Meanwhile, cosmologists are split. Inflation theory, which posits that the early universe underwent a period of exponential expansion, has had great success explaining the uniformity of the cosmic microwave background and the distribution of large-scale structures. But it also predicts the existence of a multiverse, chaotic sea of pocket universes, each with its own physical laws. This eternal inflation is mathematically sound, yet completely unobservable, placing scientists in a philosophical dilemma. Can we accept a theory that can never be tested? Does it still count as science? Some argue that the multiverse is a natural consequence of inflation and quantum fluctuations. Others say it's an escape hatch, a way to explain the fine-tuning of the universe without providing true understanding. The problem becomes even more complex with string theory, which suggests that the fundamental constituents of reality are tiny vibrating strings existing in up to 11 dimensions. String theory also allows for a multiverse but offers no current way to test it. Its mathematics are rich, its symmetry beautiful, but its connection to reality remains speculative. At the same time, observational data introduces its own contradictions. We measure the expansion rate of the universe, called the Hubble, constantiusing two different methods, one based on the early universe, through the cosmic microwave background, and another based on the local universe, using supernovae and standard candles. These two methods yield different results, a discrepancy known as the Hubble tension. It's not just a small error, it's a statistically significant difference, and it suggests that something is missing from our models. Is dark energy changing over time? Are our assumptions about the early universe wrong? Is there an unknown particle influencing the dynamics of the cosmos? No one knows yet, but the tension remains unresolved, casting a shadow over our confidence in the current cosmological model, known as Lambda CDM. This model, for all its predictive power, relies heavily on dark components, dark matter, which we cannot see, and dark energy, which we do not understand. These aren't just placeholders for ignorance. They're deeply embedded in the mathematics, and their effects are measurable. But they raise uncomfortable questions. How can our model of the universe be correct when 95% of it is made up of entities we cannot directly observe? And what if our fundamental understanding of gravity is wrong? Modified gravity theories attempt to explain galactic rotation curves and cosmic acceleration without invoking dark matter or dark energy. But so far, none have been universally accepted. Each step forward uncovers deeper layers of conflict, as if the universe itself resists easy answers. Adding to the confusion is the debate over time itself. In some cosmological models, time is infinite. In others, it emerges from a more fundamental timeless reality. The Big Bang is often described as the beginning of time. But what does that mean? If time didn't exist before the Big Bang, then how did it begin? What caused the initial conditions? Can causality exist without time? These questions pit different interpretations of quantum mechanics against each other. From the Copenhagen interpretation to many worlds to pilot wave theories, each offering a different vision of what reality really is. And if we ever do develop a full theory of quantum gravity, a unified framework that merges general relativity and quantum mechanics, it may rewrite everything we think we know, not just about the edge of the universe, but about space, time, and matter themselves. Meanwhile, the philosophical implications of these conflicts loom large. If we can't know what lies beyond the observable universe, should we even try to define it? If competing models all agree within the limits of observation, is one truer than the other? And if the universe is ultimately unknowable beyond a certain point, does that make our efforts futile? Does it elevate them, turning every act of exploration into a defiance of cosmic indifference? The very idea of the universe having an edge may be a misdirection, a symptom of our human tendency to imagine boundaries and shapes in a reality that defies both. The cosmos may have no edge at all, only limitations imposed by our perspective, our instruments, and our theories. But even in this storm of contradiction, cosmology thrives. It is the only science that allows us to study the entire universe as a single object. And the fact that our models are in conflict is not a weakness, it's a sign of vitality. Science advances through tension, through disagreement, through the relentless testing of ideas, and every unanswered question about the edge of the universe is an open door for the next generation of thinkers. The conflict is real, and it is profound, but it is also what makes cosmology so compelling. In no other field do we confront questions so big so fundamental, and so challenging. To define the edge of the universe is to define the limits of knowledge itself. And while we may never reach consensus, the journey through the unknown continues, driven by curiosity, grounded in evidence, and inspired by the dream that even in a universe of paradoxes, truth might still be within reach. What if, after all the telescopes have been built, all the data has been analyzed, and all the theories have been debated, we arrive at a single inescapable conclusion: the universe has no edge? What if the great boundary we've spent centuries searching for is nothing but a ghost, a projection of our need for structure imposed on a cosmos that does not end, does not loop, does not close because it was never meant to? That idea, deceptively simple at first glance, explodes into a web of consequences that reach into every branch of physics, cosmology, and philosophy. It forces us to re-examine the foundations of what we call reality. It challenges our need for beginnings, middles, and ends. It questions the boundaries of human understanding and opens up a view of existence that is both thrilling and deeply unsettling. Because a universe without an edge is not just an infinite expanse of stars and galaxies. It's a direct assault on the comforting idea that anything can be complete or contained, and in that realization, everything changes. In physics, the implications are immediate and profound. If the universe has no edge, no outer boundary, no definitive shape, then our models of space and time must accommodate not just vastness, but true infinity. This isn't just large-scale emptiness. It's a reality where space goes on forever in every direction, with no curvature that closes back on itself, no structure to contain it, and no central point from which it all began. While our current models, such as the Lambda CDM model, allow for an infinite universe that is flat and homogeneous on large scales, this assumption sits uneasily with quantum mechanics, which generally deals in the discrete and the measurable. Infinity is a troubling concept in science. It breaks equations, it leads to paradoxes, it resists prediction. And yet, if the universe is truly infinite, then we must reconcile ourselves with infinities not as mathematical curiosities, but as physical reality spaces with infinite mass-energy distributions, infinite repetitions, infinite versions of everything that has ever happened or ever could happen. This is the core implication of an infinite universe. If the cosmos extends endlessly and the laws of physics are uniform, then statistically, every configuration of matter must repeat. Somewhere, unimaginably far away, there is another you reading this sentence. Somewhere else, a version of Earth where dinosaurs never went extinct. And beyond that, versions of the universe so alien that even our best minds couldn't describe them. This forces a deeper re-examination of our models. Inflation theory, which predicts an exponentially expanding early universe, naturally leads to eternal inflation, and eternal inflation leads directly to the multiverse. In this framework, our observable universe is just one bubble in a foam of infinite bubbles, each with its own physical laws, constants, and outcomes. Some might be lifeless, some might be teeming with unimaginable complexity, and some might mirror ours so precisely that the only difference is a single atom's position. But here lies the tension. If we accept an infinite universe or multiverse, how do we test it? The very nature of infinity means that most of it is forever beyond our reach, lying beyond the cosmological horizon, never able to influence us or be observed. This creates a crisis in scientific philosophy. Can we meaningfully talk about things we can never see? Is a theory still scientific if it predicts unobservable infinities? Some physicists argue yes, that if a theory is the natural consequence of a well-tested framework, then we must follow it wherever it leads. Others argue no, that science must remain rooted in empirical evidence. And without testability, we risk slipping into metaphysics. The philosophical consequences are no less dramatic. If the universe has no edge, then our entire intuitive framework for thinking about existence begins to collapse. Humans evolved in bounded environmentscapes, forests, islands, planets. We understand beginnings and ends. We live and die. We build stories around arcs, cycles, finite structures. But an infinite universe has no such arc. It has no edge to find, no outside to reach. It just is. always, everywhere. And within such a reality, our traditional questions: where did it all begin? What lies beyond? What is the purpose? Start to lose meaning. Because if there is no edge, then perhaps there is no origin in the conventional sense. The Big Bang, often described as the beginning of the universe, may not be a starting point in space or even time, but a phase transition, a local event in a sea of ongoing quantum activity. Perhaps universes are constantly budding off from deeper layers of reality, like bubbles in boiling water. Perhaps our cosmos is just one fluctuation in a timeless multiversal field. If that's true, then even the word universe loses precision. What we thought was everything might only be a fraction of a much larger holon that exists beyond time, beyond space, beyond the reach of logic shaped by evolution and survival. And yet, for all its strangeness, this idea also carries a peculiar kind of liberation. A universe with no edge means there are no limits to discovery. There is always more to explore, more to understand, more to imagine. It means our cosmic story is not one of completion, but of continual unfolding. We are not approaching a final frontier, we are standing at the shore of an infinite ocean, every wave bringing new mysteries. It also reframes our role in the cosmos. In a finite universe, our place may feel central, even significant. In an infinite one, we become small, infinitesimal, even but not irrelevant, because consciousness, even if fleeting, even if rare, becomes all the more precious in a sea of repetition and entropy. If the universe will go on forever, if stars will form and die endlessly, if galaxies will dance and drift until all is dark and cold, then what we do here and now may be one of the few flickers of awareness ever to rise and ask, why? In a cosmos without edges, every question becomes an act of rebellion against the void. Every discovery, a light cast into darkness that never ends. But such a vision also exposes the limits of our current physics. General relativity, for all its beauty, does not incorporate quantum mechanics. Quantum field theory, for all its precision, does not explain gravity. We lack a theory of quantum gravity, a unified framework that can describe black holes, the Big Bang, and the birth of space and time itself. Until we find it, our understanding will remain incomplete. And if the universe has no edge, if it stretches into realms we cannot perceive or even define, then we may need entirely new tools to understand it, new mathematics, new paradigms, new ways of thinking. We may need to let go of ideas like space and time altogether and embrace frameworks where information, energy, and entanglement are the true primitives. Theoretical physics is already moving in this direction, with proposals like the holographic principle, emergent spacetime, and the ADS-CFT correspondence suggesting that space may not be fundamental at all. In these models, the universe is like a three-dimensional projection of information, encoded on a two-dimensional boundary. It's a radical idea, but one that solves many of the contradictions between general relativity and quantum theory. And if it's correct, it means our entire sense of depth, distance, and direction may be illusions emerging from something deeper. The need for new physics is not just academicate, is essential. Without it, we cannot understand the earliest moments of the universe. We cannot explain dark energy, dark matter, or the singularities that lurk inside black holes. We cannot resolve the Hubble tension or test the nature of the multiverse. And most importantly, we cannot answer the question of why there is something rather than nothing, why the universe has the properties it does, or why we are here at all. These are not just questions of curiosity, they are questions of identity. They shape our worldview, our philosophy, our place in the story of existence, and in the face of an infinite, edgeless cosmos, they become more urgent, not less. Because ultimately, a universe without an edge is not just a challenge for physicists, it is a mirror for humanity. It reflects our endless hunger for understanding, our deep discomfort with uncertainty, our stubborn refusal to accept limits. And in that mirror, we see a species that, for all its flaws, has dared to look into the void and ask the unanswerable. We see creatures made of dust and memory, writing equations in the dark, building machines to catch the faintest whispers of ancient light, and telling stories about things we may never fully grasp. And maybe that is enough. Maybe the point of the cosmos is not to be solved like a puzzle, but to be engaged with, to be questioned, explored, feared, and loved. Maybe the true edge of the universe is not out there in the sky, but in us, in our willingness to imagine more, to accept mystery, to live in awe. And in that way, perhaps we've already touched infinity not with our telescopes, not with our equations, but with our wonder. There comes a moment in every great story when the world changes not with a loud crash or sudden explosion, but with the quiet revelation of a new truth, one so profound that it alters the way we see everything that came before. In the story of the universe, that turning point came at the end of the 20th century, not from a planet-shattering discovery or a radio signal from an alien world, but from light faint, dying light from ancient exploding stars billions of light years away. These supernovae, type Ia, were used by astronomers as cosmic mile markers, bright enough to be seen across the vast reaches of space and reliable enough to act as standard candles. By measuring their brightness and redshift, cosmologists believed they could finally map the rate at which the universe was slowing down after the Big Bang. But what they found instead shook the foundations of cosmology. The universe wasn't slowing down at all, it was speeding up. This discovery, made independently in 1998 by the Supernova Cosmology Project and the High-Z Supernova Search Team, revealed that the expansion of the universe is accelerating, not decelerating, as expected. This was not a small correction, it was a complete reversal of cosmic expectations. It meant that some unseen force, was counteracting the pull of gravity on the largest scales and pushing galaxies apart faster and faster. That force was soon given a name, dark energy. And with that name came a flood of questions. What is it? Where does it come from? Why does it exist? To this day, we still don't know, but its discovery marked a turning point as dramatic as any in scientific historia, shift from a universe that was vast but understandable to one that is stranger, darker, and more mysterious than we ever imagined. Dark energy now makes up about 68% of the total energy content of the universe, dwarfing both dark matter, 27%, and ordinary matter, a mere 5%. Its presence is inferred from its effects, chiefly the accelerating expansion of space, but we have no direct detection, no laboratory evidence, and no concrete theory that explains it. Some models suggest it is a property of space itself, the so-called cosmological constant that Einstein once proposed and then famously rejected. Others propose that dark energy is dynamic, changing over time, a field known as quintessence. Still others suggest we need new physics altogether, perhaps modifications to general relativity on cosmic scales, or entirely new dimensions of reality we have yet to perceive. Whatever it is, dark energy has become the defining feature of our modern cosmological model, shaping not only the present state of the universe, but also its fate. If this expansion continues to accelerate, galaxies will drift further apart until the night sky goes dark, stars will burn out, black holes will evaporate, and the universe will end not in fire or collapse, but in a cold, silent, Faditha so-called heat death of the cosmos. But we only know any of this because of another turning point, the exponential growth of our technological power. For most of human history, our view of the universe was limited to what we could see with our eyes, and later, through telescopes bound by Earth's atmosphere. But with the launch of the Hubble Space Telescope in 1990, we opened a new chapter in our exploration of the cosmosome, where the blur of atmospheric interference gave way to crystal-clear images of galaxies billions of light years away, where we could literally look back in time to see the early universe as it was forming. Hubble's deep field images revealed a universe teeming with structural galaxies tangled in gravitational webs, colliding, forming stars, and evolving over time in ways we had only theorized. It allowed us to refine the Hubble constant, measure the age of the universe, study the life cycles of stars, and detect the gravitational lensing caused by invisible dark matter. Hubble was not just a telescope, it was a time machine, a mirror, and a revolution. And yet even Hubble had its limits. There were wavelengths of light it couldn't see infrared, especially because they were absorbed by Earth's atmosphere, or because its instruments weren't designed to detect them. To see further back, into the dust-shrouded birthplaces of the first galaxies and stars, we needed something more powerful. Enter the James Webb Space Telescope, JWST, launched in 2021 after decades of development. Unlike Hubble, JWST orbits far from Earth, shielded from heat and light, its 6.5-meter mirror folded like origami and deployed in the cold vacuum of space. With its infrared capabilities, JWST began to peer into the earliest epochs of cosmic history just a few 100 million years after the Big Bang. And what it found was unexpected. Galaxies were forming faster, earlier, and in more complex ways than our models had predicted. We expected to find small, chaotic blobs of matter slowly coalescing into structure. Instead, JWST found surprisingly well-formed, massive galaxies at redshifts we didn't think were possible, challenging assumptions about how quickly matter organized itself in the early universe. These findings, still being analyzed, may force revisions to our understanding of cosmic evolution, structure formation, and the role of dark matter and feedback processes in galaxy growth. But they also raise tantalizing possibilities. Are we missing something fundamental about the early universe? Could our models of inflation, dark matter, or even cosmic time be incomplete? And it's not just galaxy formation that JWST is revolutionizing. It's studying the atmospheres of exoplanets' worlds, orbiting distant stars looking for chemical signatures that could hint at biological activity. It's observing star formation in unprecedented detail, probing the disks of dust and gas where planetary systems are born. It's measuring gravitational lensing with precision that could help map the distribution of dark matter more accurately than ever before. In every field it touches, JWST is pushing the boundaries, revealing a cosmos that is at once familiar and alien. This is the new era of astronomy driven not just by ideas, but by machines that extend our senses to places and times we could never reach on our own. And it's not alone. Other instruments like the Vera-C Rubin Observatory, set to begin operations soon, will scan the entire sky repeatedly, creating dynamic maps of the changing universe, detecting transient phenomena, and possibly discovering new classes of objects altogether. Gravitational wave observatories like LIGO and Virgo have already begun a new chapter in physics, detecting the ripples of space-time caused by colliding black holes and neutron stars, and future detectors will probe even deeper into the violent history of the universe. Meanwhile, missions like Euclid and the Nancy Grace Roman Space Telescope will map the geometry of space and the evolution of cosmic acceleration with unprecedented clarity, providing new data on dark energy, dark matter, and the overall shape of the cosmos. Taken together, these technological advances represent a profound turning point in our understanding. For the first time, we are beginning to confront not just what the universe is, but how it came to be, what it is made of, and what its ultimate destiny might be. We are probing the edges of knowledge, not just spatially, in terms of how far we can see, but conceptually, in how deeply we can understand. And yet, for all our progress, each answer brings new questions. Why does dark energy exist? Why did inflation happen? Why is the universe so flat and smooth on large scales? What is the true nature of time and space? What happens inside a black hole? What caused the Big Bang, or was there something before it? The turning point, then, is not just a moment of discovery, it is a shift in perspective. It is the realization that we are now confronting questions that blur the line between physics and philosophy, science and metaphysics. It is the dawning awareness that the cosmos is not just bigger, older, and stranger than we thought, but that it may be fundamentally unknowable in ways we're only beginning to grasp. And yet, we keep going. We keep building better instruments, writing better equations, asking better questions, because the story of the universe is not finished. It is still unfolding, one photon, one particle, one observation at a time. And we are part of that story, not its center, perhaps, but its eyes, its voice, its mind. The turning point is not the end. It is the beginning of something greater. A new era of cosmic understanding, a deeper dive into the unknown, a journey that has only just begun. What if, in our pursuit of the universe's deepest secrets, we've been asking the wrong questions all along? What if the limitations we keep encountering, the mathematical paradoxes, the observational boundaries, the theoretical collisions aren't signs that the universe is resisting our understanding, but clues that we need to shift the very framework in which we approach the cosmos. For centuries, we've tried to map space and time like explorers, charting an ocean, measuring distances, tracing trajectories, observing light as it travels across a seemingly three-dimensional universe. We've pictured the universe as something out there, a grand external object unfolding through time. But what if that picture is incomplete? What if reality as we perceive it is not fundamental, but emergent like a hologram, a projection of something deeper and more abstract? In the last few decades, science has begun entertaining these radical alternatives, and they have fundamentally reshaped the way we think about cosmology, space-time, and the universe's structure, not by adding more data to the old model, but by flipping the model itself. Among the most mind-bending of these ideas is the holographic principle, the notion that everything we perceive as three-dimensional might actually be encoded on a two-dimensional boundary at the edge of the universe, much like a hologram projects 3D images from a 2D surface. This principle, first proposed in the 1990s by physicists Gerard T. Hooft and Leonard Susskind, emerged from the study of black holes, particularly in response to the black hole information paradox, which asked what happens to information about particles that fall into a black hole. According to classical physics, that information would be destroyed, a violation of the laws of quantum mechanics, which demand that information be conserved. But if all the information about the matter that enters a black hole is stored on its event horizon, its two-dimensional boundary, then the information isn't lost. It's just smeared out across the surface, waiting to be reinterpreted. This insight led to the realization that perhaps the same could be true for the universe itself. If a black hole can store three-dimensional information on a two-dimensional boundary, then perhaps the entire universe behaves like a black hole in reverse massive, expanding entity whose interior is encoded on a cosmic horizon. In 1997, Juan Maldacena's groundbreaking work on AD-CFT correspondence provided a concrete mathematical framework for this idea, demonstrating that a universe with gravity in a bulk space can be equivalent to a gravity-free quantum field theory on its boundary. Though this specific correspondence involves an idealized universe, anti-de Sitter space, that differs from ours, it cracked open a new way of thinking, that space-time and gravity themselves might not be fundamental, but emerge from lower-dimensional, information-based processes. This represents a profound shift in perspective. Rather than thinking of particles and forces as the building blocks of reality, we begin to consider information as the true substrate. In this view, space is not an empty stage, where physics happens. It is a construct, a derived concept that emerges from entangled quantum information. Distance, locality, even causality may be illusions produced by deeper, non-spatial dynamics. Quantum entanglement, long considered a quirky phenomenon where particles communicate instantaneously across vast distances, may actually be the glue that holds space-time together. Researchers like Mark van Ramsdonk have suggested that entanglement is geometry, and that changes in the entanglement between quantum systems literally warp the shape of space. So what does this mean for cosmology? For starters, it may mean that the Big Bang itself is not a beginning in space and time, but a kind of phase transition, a quantum event in a timeless background that gave rise to space-time as an emergent phenomenon. It may also change how we interpret the cosmological horizon. If our universe is a hologram, the observable boundary of what we can see might not be a limit of light speed and age. It might be where the information that encodes our universe is stored. The implications are staggering. We might be inside a cosmic hologram, decoding patterns on its surface with every observation we make. The edge of the universe, then, is not a place in space. It's a boundary of data, a horizon of computation, a limit not of distance, but of dimensional translation. This shift also reshapes the scientific conversation itself. It forces physicists to bridge the divide between quantum mechanics and general relativity, not by smashing them together, but by asking whether both are emergent from a deeper principlion where gravity, space, and time are side effects of information dynamics. Instead of trying to unify gravity and quantum theory in the traditional sense, scientists are now exploring frameworks like quantum information theory emergent space-time models, and entropic gravity. Eric Verlinde's work, for example, proposes that gravity is not a fundamental force, but a statistical effect in emergent phenomenon, arising from the thermodynamics of information, like heat arises from molecular motion. In such a framework, Newton's laws and even Einstein's equations are approximations of deeper, informational laws that govern the way bits of data arrange themselves in the cosmic code. At the same time, these ideas raise philosophical questions that stretch the boundary between science and metaphysics. If space and time are not fundamental, what is? If consciousness and observation are necessary to collapse quantum probabilities into experienced reality, are we co-creators of the universe? Is reality objective, or is it a product of informational relationships between observer and observed? While most physicists are cautious about venturing into such territory, the observer problem in quantum mechanics, where outcomes depend on measurements that reality may be inseparable from the process of perception. And if the universe is informational, then perhaps the very act of observation reshapes the geometry of space itself. In this light, experiments like quantum teleportation, superposition, and delayed choice quantum erasers aren't just curiosities. They're windows into the machinery behind the curtain, hints at the rules of a deeper game we are only beginning to perceive. Moreover, this shift in thinking forces us to reconsider our relationship to the cosmos. If the universe is not a vast expanse we float through, but a pattern we're part of, an emergent construct that includes our bodies, minds, and perceptions, then the line between out there and in here begins to blur. The universe is not just external, it's internal. Its rules are not just imposed upon us, they are co-written with us. This isn't a retreat into solipsism or mysticism, it's a recognition that the old categories of observer and observed are breaking down under the weight of quantum interconnectedness. The edge of the universe may not be a distant boundary, but a limit of perspective, a horizon of awareness that grows as we understand more, calculate more, entangle more. And while these ideas remain speculative, they are increasingly supported by data-driven puzzles in cosmology. The unexplained early formation of massive galaxies, observed by the James Webb Space Telescope, the mysterious acceleration caused by dark energy, the apparent flatness and uniformity of space despite causal separation, and the quantum fluctuations that seeded cosmic structure all suggest that traditional geometric models of spacetime may be insufficient. The very smoothness of the cosmic microwave background, its temperature variations measured down to microkelvins, is better explained by inflation, a theory itself rooted in quantum fields, hinting again that the seeds of structure were quantum in origin. Structure arose not from classical seeds, but from quantum randomness, expanded and frozen into the fabric of space by cosmic inflation. That means the very large-scale shape of the universe is written by the tiniest possible scales of reality, Planck-level fluctuations, quantum scribbles magnified into galaxies. This is why quantum mechanics is no longer confined to particle physics or atomic models. It is increasingly viewed as central to the architecture of the universe itself. From the inflationary epoch to black hole thermodynamics, from the entropic bounds of information storage to the quantum entanglement that may construct space, quantum principles are woven into the fabric of the cosmos. They no longer just describe matter, they explain why space-time exists at all. This changes how we define fundamental. Once, particles were fundamental, then fields. Now, perhaps it's bits of information, qubits, entanglement networks, tensor diagrams. We are entering an age where quantum gravity may not be about quantizing space, but about discovering how space arises from quantum behavior. And so, the shift in perspective continues. The classical view of the universe as a vast machine governed by absolute laws is giving way to a universe seen as a process, a computation, a network. The tools we use, whether string theory, loop quantum gravity, or tensor networks, are not just mathematical models. They are metaphors for understanding a reality that may not be accessible through space and time at all. The edge of the universe, then, is not a location. It is a transformation. A place where geometry becomes algebra, where motion becomes correlation, where space becomes information. And if we follow this path, we may not find a wall, or a loop, or a tear in the fabric of the cosmos, may find a mirror, reflecting not just the structure of the universe, but the structure of the human mind, reaching beyond its limits into the next frontier of thought. What if everything we thought we knew about the universe, its size, its rules, its origin turned out to be only a fraction of the truth? What if our most trusted theories, the very models that carried us from the Earth to the Moon, from the atom to the stars, were only accurate within a narrow range of conditions, a sliver of reality carefully selected by chance or design? Science has always advanced by confronting unexpected data, but in recent decades, those surprises have grown larger, stranger, and harder to explain within our established frameworks. And as each new mystery unfolds, we begin to sense a much bigger story waiting beneath the surface, one where our universe is not alone, where the rules of physics are not universal, and where the very fabric of reality may be synthetic. This is the unexpected twist in the tale of the cosmos. The realization that we may not be living in the only universe or even a fundamental one, and that our entire existence could be just one small ripple in an ocean of possibilities. It began, as many scientific twists do, with data that didn't quite fit. The accelerating expansion of the universe, discovered in the late 1990s, was the first blow. It revealed that something unseen dark energy was pushing galaxies apart faster and faster, contradicting every intuitive notion of how gravity should behave on cosmic scales. Then came the Hubble tension, a growing inconsistency between different measurements of the universe's expansion rate. Measurements from the early universe, based on cosmic microwave background data, didn't match observations from the late universe, such as supernovae and galaxy surveys. The discrepancy was small at first, then became statistically significant, then impossible to ignore. It wasn't just a measurement error, it was a signal. Something in our models was wrong. And that's when cosmologists began to wonder, what if the universe we observe is just a particular realization of many? What if there are other universes with different expansion histories, different physical constants, different rules altogether? Enter the multiverse, a word once confined to the realm of science fiction, now discussed seriously in scientific journals, conference rooms, and theoretical frameworks. In the context of inflationary cosmology, the multiverse is not just plausible, it's expected. Inflation, the exponential expansion that smoothed out the early universe, may have occurred not just once, but endlessly, spawning bubble universes in a frothing sea of quantum fluctuations. Each of these pocket universes could be completely isolated from the others, with its own version of physical laws. Some might be empty, others unstable, and a few like ours rich with structure, stars, life. In such a picture, our universe is not the universe. It's a local region with specific properties, selected not by destiny or necessity, but by probability. And this changes everything. It reframes the fine-tuning problem, where physical constants like the strength of gravity or the mass of the electron appear precisely calibrated for life. In a multiverse, there's no need for a special explanation or universe, just happens to be one where life is possible, because only such universes can be observed in the first place. This is called the anthropic principle, and while it may sound circular, it's statistically coherent. Among infinite outcomes, observers only arise where conditions permit them. But the multiverse isn't the only strange twist. Another, more radical idea has begun gaining traction that doesn't posit other universes, but instead questions the very reality of this one. It's called the simulation hypothesis, and it suggests that our universe might not be fundamental at all, but a computational constructive simulation run by an advanced intelligence for purposes unknown. First proposed seriously by philosopher Nick Bostrom in 2003, the argument is deceptively simple. If it becomes possible for a civilization to simulate conscious beings in a digital environment, and if they run many such simulations, then statistically speaking, we are more likely to be in one of those simulations than in the original base reality. The logic doesn't depend on faith or conspiracy, it's a probabilistic reasoning rooted in technological possibility. And while there is no direct evidence that we are in a simulation, some physicists and philosophers take the idea seriously, pointing to features of our universe that seem oddly compatible with a digital origin. Quantized space and time, limits to information density, like the Bekenstein bound, and the mathematical nature of physical laws. Some even argue that certain glitches in quantum mechanics, such as wave function collapse, non-local entanglement, or the observer effect, could be interpreted as signs of a rendered reality, where outcomes resolve only when measured, like pixels updating when a character turns their head in a video game. Others note that our universe's constants are so finely tuned that even minor changes would render it lifeless, suggesting either deliberate design or selection bias across many iterations. Of course, simulation theory remains speculative, and most physicists are cautious. But the fact that it's even being entertained reveals how profoundly our understanding of reality has shifted. Where once the universe was assumed to be singular, eternal, and objective, we now consider that it may be relative, layered, and contingent. These unexpected ideas, multiverse theories, simulation hypotheses, emergent spacetime have triggered a deeper realization about our place in the cosmos. They suggest that what we experience as physical reality is not the ultimate stage of existence, but a subset, a projection, or an emergent effect. And with that realization comes a kind of existential vertigo. If the universe is infinite, and we are one of many versions of ourselves, does identity still matter? If we're in a simulation, what is consciousness code, or something more? If our laws of physics are not universal, but local, then what lies beyond the bubble we inhabit? These are not questions science can yet answer definitively, but they have begun to reshape the tone of scientific inquiry itself. No longer is the goal simply to find the edge of the universe or the beginning of time. Now, the goal is to understand why those questions may be limited, why our intuitions may be misleading, and how reality behaves in frameworks far beyond the classical. One of the most striking outcomes of this twist is the realization that our mind-sour consciousness might be more central to this mystery than we once believed. In traditional physics, observers were irrelevant. In quantum mechanics, observers collapse wave functions. In the holographic principle, information depends on boundaries. In simulation theory, the act of observation might be the trigger for rendering. Across all these models, the boundary between subject and object, between knower and known, is blurring. And in that blurring, a new picture of reality emerges, zone where participation matters, where perspective shapes what is real, and where our curiosity is not just a tool, but a fundamental part of the universe's unfolding. And perhaps that's the final twist, not that we are small and insignificant in a cold mechanical cosmos, but that we are participants in a reality so vast, so intricate, and so mysterious that our questions, our thoughts, and our very act of wondering might be woven into the structure of existence itself. Maybe we are not outside the universe, observing it. Maybe we are inside the equation, a part of the logic, a consequence of the laws, and a spark of something more, consciousness, reflecting upon its own possibility. The unexpected twist, then, is not just that reality is stranger than we thought. It's that we are stranger than we imagined, and that in our endless search for the edge of the universe, we may one day discover that what we were really searching for was the source of the question, the place within ourselves that dared to ask in the first place. As breathtaking as our cosmic journey has been, from the first telescopic glimpses of the heavens to the cutting-edge data streaming in from deep space today, we now stand at a moment where the questions have become bigger, stranger, and more complex than ever, and so too have the challenges. With each breakthrough comes a new wall to climb. Every answer opens 10 more doors. And while we've entered an era of precision cosmology, where many measurements are accurate to a fraction of a percent, we are now grappling with the realization that knowing more isn't always the same as understanding more. The universe has revealed itself to be not just vast, but profoundly mysterious, filled with forces we don't understand, dimensions we can't observe, and phenomena that defy even our best theories. This is the frontier where the boldest minds now work and where the next generation must go further. But to get there, we must first overcome some truly immense obstacles, both technological and conceptual. One of the most immediate challenges facing cosmology and astrophysics today is the limitation of our observational technology. For all the brilliance of instruments like the James Webb Space Telescope, we remain confined to a small window of wavelengths and a small portion of the electromagnetic spectrum. Much of the universe is still effectively invisible to us, obscured by dust, hidden behind energetic processes, or existing in spectra we haven't yet fully accessed. Radio telescopes can peer through some of this, revealing the cool gas that shapes galaxies, while X-ray and gamma-ray observatories expose the violent births and deaths of stars. But no single instrument can see the full picture, and even the best telescopes are ultimately limited by their location, sensitivity, and resolution. We can only see what our instruments allow us to see, and that means the universe's earliest moments, the exact mechanism behind dark energy, or the true nature of black holes remain frustratingly out of reach. Consider cosmic inflation, the theory that the universe expanded faster than light in the first moments after the Big Bang. It elegantly explains the uniformity of the cosmic microwave background and the distribution of large-scale structure, but direct evidence remains elusive. To confirm inflation, scientists need to detect a very specific kind of signal, primordial gravitational waves ripples in spacetime created during that expansion. These would leave an imprint on the polarization of the cosmic microwave background. And while projects like BICEP and Planck have searched for this signal, they've yet to find definitive proof. Future missions, such as the LightBird satellite or CMBS-4, are being designed to look deeper, but detecting these signals requires a sensitivity and precision beyond what we currently possess. It's not just about building better telescope it's about pushing the edge of what's technologically feasible. The same is true for understanding dark matter. Despite decades of effort, no one has directly detected a dark matter particle. Experiments buried deep underground, like Lux, Zeppelin, or Xenont, wait patiently for a telltale interaction, a single flash of light, a subtle vibration, but so far, nothing. This absence raises troubling questions. Are we looking for the wrong thing? Is dark matter made of something other than WIMPs, weakly interacting massive particles? Could it be primordial black holes? Sterile neutrinos? Or is our understanding of gravity itself flawed at large scales? To find out, we need new detection methods, new particle accelerators, and perhaps most critically, new theories. The Large Hadron Collider, while revolutionary in its discovery of the Higgs boson, has so far failed to uncover anything beyond the standard model of physics, suggesting that we may need entirely new frameworks to make progress. And then there is dark energy, arguably the greatest mystery in modern cosmology. It dominates the energy content of the universe, drives its accelerated expansion, and yet we have no clue what it is. Is it a constant property of space, as Einstein once proposed? Is it dynamic? Does it decay? Could it be a sign that our entire model of gravity breaks down on cosmic scales? Missions like Euclid and the upcoming Nancy Grace Roman Space Telescope aim to chart the expansion history of the universe in exquisite detail, measuring the geometry and structure of space across billions of years. By doing so, scientists hope to uncover patterns that might reveal the fingerprints of dark energy's true nature. But these observations, as powerful as they are, still rely on interpreting light from distant objectstiny signals swamped by noise, redshift, and cosmic dust. They also depend on the accuracy of our current theoretical models. If those models are incomplete, we may misread the data, reinforcing incorrect conclusions simply because we lack a better framework. This is why the next generation of research must go beyond building better machines. We must also build better ideas. New physics is needed, not just tweaks to old models, but deep conceptual revolutions. Quantum gravity remains the holy grail, a theory that merges general relativity and quantum mechanics into a coherent whole. But after decades of work, we still don't have it. String theory offers one possibility but lacks testable predictions. Loop quantum gravity takes a different path, suggesting space-time is quantized at the smallest scales, but again, it struggles to connect with observable phenomena. More recently, emergent space-time theories, like those built on quantum entanglement or tensor networks, suggest that space and time might not be fundamental at all. These ideas are exciting, but they're also fragile, built on speculative assumptions, with little experimental guidance. To bridge this gap, scientists are increasingly looking to quantum information theory as a possible Rosetta Stone. In this approach, space-time and gravity might emerge from the entanglement of quantum bits, the smallest units of information. This reframes the universe as not a physical structure, but a computational one, where geometry is a byproduct of information flow. If these models prove viable, they could offer a new lens through which to interpret black holes, the early universe, and even the apparent fine-tuning of physical constants. But developing this line of inquiry requires new mathematical tools, new types of experiments, and new ways of thinking that challenge the assumptions physics has relied on for over a century. In parallel with theoretical advances, space exploration remains critical. The farther we can send our instruments, the more clearly we can see and possibly feel the structure of the universe. Proposals for massive interferometers in space, like the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from mergers that happened billions of years ago, including signals from supermassive black holes, and possibly even echoes from inflation itself. Missions like LUVOIR, a proposed ultra-powerful optical telescope, could detect Earth-like planets around distant stars and analyze their atmospheres for biosignatures in an indirect way to explore whether life is a cosmic inevitability or a rare accident. And then there are the even more speculative ideas: interstellar probes, quantum communication satellites, even AI-assisted observatories that could filter through oceans of data to find the faintest anomalies, the clues that could rewrite everything. But all of this faces one massive shared obstacle: resources. Building these next-generation instruments isn't just a technical challenge. It's a political, economic, and social one. Space missions take decades to plan, fund, and launch. Research budgets are finite, and scientific priorities often compete with national agendas. International collaboration is essential but fragile, and even when funding is secured, the complexity of these projects means delays are inevitable, instruments fail, and hopes must sometimes be recalibrated. That's why another key challenge for the future is sustained vision, the will to continue exploring even when answers come slowly or not at all. And yet, despite these challenges, scientists are not backing down. Plans are already in motion. The Square Kilometre Array, the world's largest radio telescope, will peer into the cosmic dawn. The extremely large telescope will offer resolutions orders of magnitude better than current ground-based observatories. New generations of detectors will push the limits of neutrino and gravitational wave astronomy. And on the theoretical side, researchers are developing new models of the multiverse, refining simulations of galaxy formation, and exploring exotic hypotheses like axions, extra dimensions, and time-symmetric physics. AI and machine learning are already transforming how data is analyzed, accelerating discovery in ways no single human could manage. The frontier is still alive, and scientists are still pushing forward, driven by the same curiosity that first made us look up at the stars. In the end, the greatest challenge may not be the technology, or the theory, or the budget. It may be the limits of human imagination. We are a species evolved for survival on the savannah, trying to decode the birth of time, the nature of space, and the shape of infinity. Our minds are remarkable, but they are also bounded by history, language, and instinct. To meet the next horizon, we may need to think in entirely new ways, to learn to imagine beyond imagination, to see not just what is, but what could be. The universe will not hand us its secrets easily, but that is what makes the search so noble, so necessary, and so endlessly human. The questions are bigger than ever, the answers are further away, but the journey, it's just beginning. The search for the edge of the universe, whether physical, conceptual, or philosophical, has become more than just a scientific endeavor. It is a confrontation with reality itself. As we arrive at the furthest reaches of observation and theory, we find ourselves surrounded not by clarity, but by contradiction. Competing models of the cosmos clash at the intersection of the very large and the very small, where black holes meet quantum particles, and where time itself may cease to be meaningful. The theories that now dominate the conversation are not minor variations of a single idea, but fundamentally different visions of what the universe is and how it works. This is the final confrontation, a moment when science must confront the limits of its own frameworks, when the pursuit of a boundary forces us to question what boundaries even mean. On one side of the battlefield is general relativity, Einstein's grand theory of gravity. It describes the cosmos as a smooth, four-dimensional fabric of space and time, warped by mass and energy. It has passed every observational test with flying colors, from the bending of light around massive objects to the ripples of gravitational waves. It tells us how stars live and die, how galaxies dance, and how black holes collapse. But it is silent on the quantum level. It cannot describe what happens inside a singularity. It does not include the uncertainty, probability, and superposition that define the quantum world. On the other side is quantum mechanics, the most successful framework in the history of physics when it comes to predicting behavior at the smallest scales. It explains the behavior of atoms, molecules, and subatomic particles with stunning precision. It underlies everything from chemistry to electronics to the structure of the periodic table, but it has nothing to say about gravity. And when pushed to extremes such as in the early universe or inside a black hole, its principles seem to break down or contradict what relativity says must happen. At the heart of this conflict is a series of paradoxes. What happens at the singularity of a black hole? What existed before the Big Bang? Can information be destroyed? Or is it somehow preserved across time and space? These questions cannot be answered by relativity alone, nor by quantum mechanics alone. They demand a unified theory, one that includes both gravity and quantum phenomena in a single coherent picture. For decades, physicists have been chasing this holy grail of modern science, a theory of quantum gravity, and in doing so, they've developed several powerful but competing frameworks. One of the most prominent is string theory, which posits that all particles are not point-like dots but tiny vibrating strings, whose vibrations correspond to different fundamental forces in particles. String theory naturally includes gravity, requires extra dimensions of space, and can reduce to both general relativity and quantum field theory under certain conditions. It is elegant, mathematically rich, and filled with potential, but it also suffers from a lack of testable predictions. Its vast landscape of solutions, each describing a different possible universe, makes it hard to know which one, if any, corresponds to ours. Critics argue that without empirical evidence, string theory remains speculative. Supporters counter that its mathematical consistency is itself a clue to its truth. An alternative approach is loop quantum gravity, which takes a very different route by attempting to quantize space itself. It suggests that space is made up of tiny discrete loops of quantum information, woven together like a cosmic fabric. In this model, space and time are not continuous but granular, like pixels on a screen. It avoids some of the infinities that plague other models and offers a clear conceptual framework for how space-time might emerge from quantum interactions. But loop quantum gravity has its own limitations. It struggles to connect with particle physics and lacks the unifying elegance that string theory offers. Then there is the holographic principle, born out of black hole thermodynamics and championed by thinkers like 't Hooft, Susskind, and Maldacena. It proposes that everything we experience in 3 dimensions, including gravity, may be a projection of information encoded on a 2-dimensional surface. The best mathematical example of this is the AD-S CFT correspondence, which shows a precise equivalence between a gravity theory in a 5-dimensional anti-de Sitter space and a quantum field theory on its 4-dimensional boundary. While our universe is not an AD space, the principle offers tantalizing hints that space and gravity are emergent phenomena, not fundamental ones. These approaches, string theory, loop quantum gravity, holography, are not mutually exclusive. In fact, some physicists hope that a deeper theory may unify them, revealing that they are different aspects of the same underlying truth. But so far, no such master theory has emerged. Instead, what we see is a scientific community divided into camps, each with their own insights, strengths, and limitations, each searching for a breakthrough that will bring everything together. Meanwhile, cosmology itself is undergoing a transformation. The discovery of dark matter and dark energy components that make up 95% of the universe's contentas forced scientists to reconsider the basic assumptions of their models. Dark matter is invisible and undetectable, except through its gravitational effects. Dark energy, even more mysterious, appears to be driving the accelerated expansion of the universe. We know they exist, but we don't know what they are. Are they new particles, new fields, emergent phenomena, or signs that our understanding of gravity is fundamentally flawed? Add to this the Hubble tension, the discrepancy between the universe's expansion rate, as measured from the early universe via the cosmic microwave background, and from the late universe via supernovae, galaxies. The tension has persisted and strengthened, hinting that our models may be incomplete or that we are missing something vital about how the universe evolves. These are not small disagreements, they strike at the foundation of the standard model of cosmology. Some researchers suggest that we need new physics, possibly involving exotic particles or interactions. Others argue that we need to re-examine our assumptions about time, space, and causality itself. And looming behind all of this is the question of the boundary. Does the universe have an edge, a physical limit, a metaphysical line, a conceptual horizon? If the universe is infinite, what does that mean? If it's finite, what lies beyond? Can we ever reach the edge? Or is it receding faster than light itself? Is there an edge in time, rather than space, a point before which nothing existed? Or is time itself an emergent illusion, a byproduct of entanglement and entropy? These are not idle questions. They affect how we build our models, interpret our data, and imagine the future of science. Despite all this, the future of cosmology is bright, not because we are close to final answers, but because we are finally asking the right questions. The next few decades will see the launch of powerful new instruments. The Nancy Grace Roman Space Telescope, which will map the geometry of space with exquisite precision. The Vera C. Rubin Observatory, which will survey the entire sky repeatedly, catching transient events and expanding our catalog of galaxies. The Laser Interferometer Space Antenna, LISA, which will open a new era of gravitational wave astronomy, listening to the echoes of the early universe and possibly even inflation itself. These tools will generate data at an unprecedented scale, and with them, we may be able to test the most ambitious ideas of modern physics. But the real revolution may come not from instruments, but from ideas, from those willing to rethink the most basic assumptions of physics, to combine the insights of quantum theory, relativity, information theory, and thermodynamics into a new paradigm. We may discover that space and time are not continuous, that the universe is not a single entity, but part of a multiverse, that reality is not built on particles but on quantum entanglement, or that consciousness itself plays a role in shaping what is real. These ideas sound radical, and they are, but they are not fantasy. They are the cutting edge of science, born from decades of paradoxes, puzzles, and quiet realizations. The final confrontation, then, is not between us and the universe, but between different visions of the universe itself. Will there ever be a single, unified theory that explains everything? Or will science remain a patchwork of models, each useful within a certain domain but incomplete in the whole? Will we ever truly know what space is, what time is, what reality is? Or will we forever be chasing shadows on the wall of a deeper, hidden structure? Whatever the answer, one thing is certain: we are in the midst of a grand transition. The old models, while still powerful, are showing their cracks. The new ones are just beginning to take shape. And in between lies a moment of wonder, uncertainty, and limitless potential. We may never find a final boundary. We may never reach the edge. But in trying, in searching, in imagining, we continue the oldest and most noble journey of all, the journey to understand where we are, who we are, and what lies beyond the veil of the known. The future of cosmology is not just about the universe. It is about us, our tools, our minds, our questions, and our endless hunger to know. What does it truly mean to look up at the night sky and ask, what's out there? Is it merely a scientific pursuit and exercise in observation, measurement, and modeling? Or is it something deeper, something profoundly human? From the earliest days, when our ancestors traced constellations into the heavens and built monuments aligned with the stars, the desire to understand the cosmos has been inseparable from our identity. It has shaped our myths, guided our migrations, and inspired our revolutions in thought. But as we've evolved from stargazers to physicists, from sailors guided by Polaris to engineers launching telescopes beyond Earth's atmosphere, one truth has remained. We explore not only to understand the universe, but to understand ourselves. And if there is one moral takeaway from the story of cosmic exploration, it is this: that in reaching for the unknown, we become more aware of what it means to be human. At its core, curiosity is a moral force. It drives us to question what is, to challenge what has been, and to imagine what could be. It is curiosity that dismantled the belief in a geocentric universe, that questioned the authority of dogma, that dared to suggest the Earth is not the center of everything. That same curiosity built telescopes, probed the nature of light, uncovered the laws of motion and relativity, and sent fragile metal ships across the void. Curiosity asks not because it always expects an answer, but because not asking feels like a betrayal of the mind's potential. In this way, science is not cold or clinical, it is passionate, stubborn, restless. It is the story of a species that refuses to settle, that finds comfort not in certainty, but in discovery. And yet, every discovery brings with it a confrontation with mystery. The more we learn, the more we realize how much remains beyond our grasp. The universe is not a riddle to be solved, but a landscape to be explored and sometimes to be revered. As we've mapped galaxies, measured the cosmic microwave background, and uncovered the nature of dark energy and dark matter, we have not closed the book on mystery. We have opened new chapters. This balance between knowledge and the unknown is one of the most powerful lessons of cosmic exploration. It teaches humility. For all our brilliance, we are still limited by time, by tools, by the architecture of our minds. And yet, it teaches us pride too. For in spite of those limits, we've looked into the abyss and begun to describe it. We've traced the story of everything back to the first fractions of a second. We've imagined realities beyond our own. We've turned chaos into structure, silence into theory, light into language. But perhaps the greatest moral lesson is found not in the answers we seek, but in how we seek them. Scientific exploration requires a deep respect for truth, for evidence, for the process of questioning and refining ideas. It demands honesty, patience, and a willingness to admit when we are wrong. In an era of misinformation and ideological rigidity, this mindset becomes not just a scientific virtue, but a social one. If we can embrace the scientific spirit in our broader lives, if we can accept uncertainty, value evidence, and prioritize understanding over assumption, perhaps we can build not only better models of the cosmos, but a better society. The ethos of cosmology is deeply moral. To question deeply, to listen closely, and to imagine bravely. Cosmic exploration also reminds us of our shared humanity. The universe does not recognize borders, flags, or ideologies. It stretches out equally above every nation, every people, every language. The photons arriving from a distant galaxy do not care whether they strike a telescope in California, Chile, or China. The questions they provoke belong to all of us. And while the history of science has sometimes been shaped by competition, its greatest achievements are always collective. The search for cosmic truth transcends divisions. It unites us in a common narrative, one where every human is a stardust-born participant in a cosmic unfolding. When astronauts first looked back at Earth from space, they didn't see nations or politics. They saw a fragile, glowing orb suspended in blackness, a home too precious and interconnected to ignore. This overview effect has inspired movements for peace, environmental responsibility, and global cooperation. It is a reminder that in the grand context of the cosmos, the differences between us are vanishingly small, and the need to care for each other across cultures, across generations, becomes moral necessity. There is also a deeper existential takeaway. The universe, in all its scale and strangeness, does not appear to have been made for us. There is no signet, at least not yet, of divine orchestration or cosmic intent. We exist in a place where galaxies drift apart, where stars are born and die, where black holes swallow light, and where time may one day run out altogether. And yet, against all odds, we are here. A fragile, intelligent species capable of thought, of emotion, of reflection, of wonder. We are the universe becoming aware of itself, poetic truth with profound moral implications. For if we are rare, or even unique, in the vast expanse of existence, then life is not just valuable, it is sacred. Every mind is a miracle. Every life is a testament to improbability. And every act of preservation, of compassion, of creation, becomes an act of cosmic significance. In this sense, the moral meaning of cosmic exploration is not about escaping Earth or mastering nature. It is about awakening to responsibility, to the preciousness of life, to the fragility of our planet, and to the possibility that our brief moment in cosmic time might hold more meaning than we ever imagined. As we contemplate other planets, other stars, other potential civilizations, we are also invited to reflect on how we treat our own. Are we stewards of our world or its exploiters? Are we architects of peace or engines of division? Do we invest in the future or burn it for the sake of the present? These are not scientific questions, but they are the questions that science leads us to ask. And finally, there is one more Lasona lesson about hope. The universe is immense. It is ancient. It will likely outlive us, but it is not indifferent. For in it, there exists at least one species that has begun to dream, to reach, to understand. That species is us, and no matter how small we are in size or time, that capacity to ask, to seek, to imagine is a victory against entropy. It is a light in the darkness. We may never find all the answers. We may never reach the edge, but we are trying. And that trying, that pursuit of the unknown, not because it is easy, not because it is profitable, but because it is in our nature, is the most human act of all. In the end, the cosmos may not offer meaning, but through it, we can make meaning. We can choose to live with curiosity, with reverence, with courage. We can tell stories not of dominion, but of discovery, not of control, but of connection. We can teach our children not just facts about the stars, but values forged in their light: humility, wonder, compassion, and awe. We can remind ourselves, every time we look up, that we are not just passengers on a rock. We are part of a universe that is still unfolding, still surprising, still singing. And in that song, if we listen closely, we may hear the echo of a deeper truth, the moral heartbeat of exploration, that the search itself is sacred, and that in the vast silence of the cosmos, our questions matter. After everything we've uncovered, the centuries of stargazing, the equations etched onto blackboards, the satellites orbiting Earth, and the telescopes peering into time, one question still remains. Should we hope for a final answer? Should we seek a closed conclusion to the story of the universe? Or is there greater value in letting the mystery remain open-ended? Science, by nature, is a pursuit of answers. But in the realm of cosmology, the deeper we dig, the more we uncover not certainty, but layers upon layers of complexity and wonder. It is tempting to imagine that one day, we will arrive at a theory of everything, a perfect, unified model that neatly explains the cosmos, its origin, its structure, its end. But is that truly the goal? Or is it more meaningful, perhaps even more power, that some questions remain unanswered? In the vastness of space, it becomes increasingly clear that not all questions are meant to be resolved. Some are meant to evolve. The edge of the universe, if it exists at all, might be forever out of reach. Not because we lack intelligence or technology, but because the cosmos itself may not be built to offer neat conclusions. The boundary could be a horizon of information, an asymptote we forever approach but never cross. In that way, the greatest scientific endeavor mirrors life itself. We don't seek to complete life. We seek to experience it, to explore it, to grow from it. Perhaps the universe is the same less a problem to be solved than a mystery to be lived. Leaving some questions unanswered is not a sign of failure, it's a declaration of potential. When Newton proposed gravity, he didn't explain what it was. He described how it behaved. When Einstein revealed relativity, he reshaped space and time but left room for quantum mechanics to challenge his ideas. Even now, as we explore black holes, dark matter, and quantum entanglement, we are not so much closing doors as opening new ones. The universe doesn't just tolerate mystery, it thrives on it. Mystery is what drives us to build better instruments, to test new theories, to challenge our assumptions, and to wonder. An open-ended cosmos invites an open-ended imagination. And with that comes the power to rethink everything from the fundamentals of physics to our understanding of consciousness and reality. One of the greatest takeaways from our journey through cosmology is that uncertainty is not a weakness, it is a source of strength. The universe is not designed to flatter human expectations. It is bigger, older, and more intricate than anything we evolved to understand. And yet, we've made astonishing progress. We've gone from thinking the stars were holes in a crystal dome to measuring the cosmic microwave background with microkelvin precision. We've turned the whispers of ancient photons into stories of birth, expansion, and death. We've mapped the shape of galaxies, uncovered the chemistry of exoplanets, and even detected the ripples of space-time itself. Each of these achievements is a triumph not just of science, but of curiosity, and none of them are the end. As we look back on the biggest themes of this exploration, a few stand out. First, the scale of the universe humbles us. Its sheer size, age, and complexity dwarf anything we can fully comprehend. And yet, this humbling perspective is a gift. It places our daily concerns into context. It inspires awe. It calls us to rise above petty divisions and see ourselves as part of something vast and beautiful. Second, the universe is dynamic. It is not static or simple, but evolving, stretching, growing, changing in ways both measurable and mysterious. The laws that govern it may themselves be emergent, the result of deeper patterns of information and structure. Third, the frontier is always moving. As our technology improves and our theories mature, the edge of the known expands, but so too does the realm of the unknown. In science, the more we see, the more we realize how much we've missed. And yet, with all this uncertainty, comes one unshakable truth. We are part of the universe. We are not separate from it, not mere spectators. We are built of its particles, shaped by its forces, animated by its energies. The iron in our blood, the carbon in our cells, the light in our eyesol come from ancient stars, long dead, whose violent deaths seeded the ingredients for life. We are, as Carl Sagan said, a way for the cosmos to know itself. And that knowledge, limited though it may be, is extraordinary. It means that the questions we ask are not just about what's out there, but also about who we are and why we wonder. This leads to one of the most profound implications of an open-ended universe: the value of imagination. When the story isn't finished, we get to write new chapters. We get to dream of worlds that might exist in other galaxies, of civilizations that may be pondering the same questions, of multiverses where different laws lead to different realities. We get to explore the limits of physics and consciousness, to build new frameworks, to ask, what else? What if? What next? And these aren't just daydreams. They are the seeds of discovery. Every breakthrough in science was once an idea no one took seriously. Every mission to space began as a sketch on a napkin, a whisper in a hallway, a what if spoken aloud. And so, we should not fear the open-endedness of the universe. We should embrace it, because finality is static. It closes the book, but mystery is alive. It keeps us reaching. It calls the next generation of thinkers, explorers, and artists to continue the work, to wonder not just about physics and stars, but about meaning, connection, and the role of consciousness in the cosmic story. In this light, science becomes more than data collection. It becomes a spiritual endeavor, not in the religious sense, but in the sense that it connects us to something greater than ourselves, something eternal, vast, and beautiful. The open universe becomes a Marora place, where we see not just galaxies and particles, but values, humility, perseverance, curiosity, and courage. So as we arrive at the end of this exploration, what should we conclude? That there is no conclusion. That space is not a puzzle with a final solution, but a journey with infinite paths. That our questions matter more than our answers. That in chasing the edge of the universe, we discover not its end, but our own beginning, a beginning of thought, of imagination, of understanding. We should take comfort in the idea that the cosmos doesn't need to be wrapped up neatly for it to be meaningful. Its mystery is its gift. Its silence is its invitation. Its endlessness is a canvas for every question we've ever dared to ask. And what of the possibilities? They remain limitless. Perhaps we will find evidence of life beyond Earth, forever altering our sense of uniqueness. Perhaps we will uncover a new theory that unifies quantum mechanics and gravity, revealing that space and time are emergent illusions, shadows of a deeper reality. Perhaps we will detect the edges of the multiverse, or prove that we are living in a simulation, or glimpse the final fate of the cosmos in the flicker of distant galaxies. Or perhaps we will never reach those heights. Perhaps the questions will remain. But even then, we will have done something remarkable. We will have tried. And in that trying, we become more than observers. We become storytellers, explorers, creators of meaning in a universe that offers none unless we build it ourselves. So let the mystery remain. Let the edge stay just beyond reach. Let the questions live on, because it is in the asking, the seeking, the wondering that we become fully alive, not just as scientists, but as humans. And in that endless pursuit, the universe reveals its final truth, that it was never about the end. It was always about the journey.